We all know that LLMs like ChatGPT and Llama 3 can generate good enough code. But can we improve the quality of the code to the level that it can be used in a competitive programming setting? Today, we are going to discuss one such paper that tries to integrate planning with code generation on large language models. So, let's get started. So we are going to look at this paper, Planning with Large Language Models for Code Generation. This was published in ICLR 2023. So in this paper, they propose a method called Planning Guided Transformer Decoding, or in short PGTD. So let's first see what is the task at hand. So let's say you have a large language model and you have a problem setting like this. Okay. So you are given in a prompt that what is the problem statement. That means, for example, in this case, you are given a string with you, you have to replace every character s with x and print the result. So you have a set of constraints on the input and output. You have the exact format of the input, the exact format of the output. Then you have a set of test input and test output. These type of settings are very common in something called competitive programming, where for example you might have seen it on website like Lead Code and Code Force, where you are given a problem statement and a corresponding very dummy and simple enough test cases. Based on that, you have to write the code and submit the code and pass that set of test cases. You are given a credit only if you pass all the test cases, right? So this is the task at hand, and this is the task they want to target. Let's see some of the responses that they get. So for example, in a standard large language model that uses a something called beam search, we will go into a little bit deeper into this, what is beam search and how it works, before we jump into how they improve beam search further, right? So based on that, if you use beam search, you get a pass rate of 0. Whereas if they use their method, which is PGTD, you get a pass rate of 1, right? So given this brief example and this motivating example where it works, let's first see what are they trying to do. Okay, so their premise is simple, that when you use a large language model for decoding, you use something called either greedy decoding or beam search, right? The problem with beam search for code generation is this. Let me go walk you through that. Okay, so let's say you are generating a sentence. You ask a language model, say that, okay, write me a story on a unicorn. That unicorn with its friends, right? And let's say it writes a story that there was a unicorn named Anna, and the Anna was working with Bob and Charlie, and so on and so forth. And then it generates a sentence, say they did some research, right? Versus there's an option to generate another sentence that Anna did some research, right? In both the sentences, because it's a generative AI task and it is a creative task, both the sentences are probably acceptable without giving any further constraints, right? You didn't give any constraints on the type of output that you want, so both the sentences would be acceptable. However, in the case of code generation, the problem is that you cannot accept certain codes if there is even a single syntax error. For example, if you are writing a code like int a is equal to 3, and you forget, in case of C, you forget to add a semicolon, then in the decoding process, this semicolon will lead to a total 100% code dump or code compilation failure, leading to 0 pass rate. So the chances of having a wrong token generated is even if it is very low, this can lead to a very high failure case. So this is the premise they give, that this is the problem with normal decoding and all. So how do you go about solving this problem is what is presented in this paper. So before we jump into that, let's first see what is beam search, right? I have created a video on that, and you can check out that video, but let me just give you a brief primer if you are in a rush. Let's say you have generated a piece of code so far like int a, right? So now what you can do is, let's say there are multiple possibilities of token to be generated, right? For example, it can be equal to, it can be semicolon, or it can be anything, right? Plus, right? Plus cannot be there because it will not compile. Let's say there are only two possibilities. One is equal to another is semicolon, right? So now what will beam search do? And let's say there are other possibilities also which are incorrect. For example, the incorrect possibility would be that plus, for example, right? So what it will do is that beam search will calculate the probability of each of these partially generated sentences so far. So for this it will generate, for this also it will generate, calculate the probability, for this also it will calculate the probability. Let's say the probability comes out to be 0.38 and this probability comes out to be 0.4, and let's say this probability comes out to be 0.0001, right? Because it is totally incorrect, right? And there can be other tokens also. There is a distribution over them also, such that it adds up to 1. Now what do? We take the top k out of these, right? Top k probabilities in the basic beam search, and let's say k is equal to 2. For in this case, what we will do is that let's say we keep these two as our possible scenarios for the future, right? So we select this one and we select this one. Now we will repeat the process again on the next step. For example, we will expand each of these twice. Let's say whatever the probability, let's say for equal to, let's say it comes out to be 3 or it comes out to be 5, right? And then in the case of semicolon, it will generate \n, and let's say it generates again after semicolon it generates another equal to. So now again we will calculate the probabilities of these partial generations. Okay, we will calculate the probability of this partial generation. Then we will also calculate the probability of this particular generation, right? And so on and so forth. For all 4 of these, we will generate the we will calculate the probabilities, and let's say the probabilities come out to be 0.3, 0.35, 0.99, because usually after semicolon the \n will be there, and for equal to, let's say the probability comes out to be 0.001. So now again out of these 4, what we will do is that we will keep 4 of k is equal to 2 of these, right? So let's say we will keep this particular one and this particular one, and we will continue doing this process for a sequence of steps till when we will do it till we generate a end of sequence token in all of the beams that we are following, right? Okay, so this is the beam search. Now what is the problem in this case? The problem in this case is that the problem with beam search is that, let's say you have generated a particular sequence, right? And this was the distribution that you followed so far. I'm doing it in an abstract manner. Okay, so let's say the probability here comes out to be 0.3. Let me use a different color here. Let's say the probability here comes out to be 0.3, 0.6, right, and 0.01, or let me just do 0.1 and 0.9. So what would you do? You will keep this one and this one because they are the top 2. Okay, so let's say you expanded these 2 again, right? Okay, now the probability values comes out to be 0.1 and 0.001, and here the probability is whatever they can come out to be, right? So now the overall probability of having this path, right? Let me just expand the one that we discarded to, right? So we discarded this one and this one. Let's say the probability distribution after, if we had chosen 0.1, could have been, let's say 0.99 and equally 0.01, right? So now the probability of selecting this particular path would have been much larger if we had not discarded this particular node. So if we made some mistake, the problem with beam search is that if we made some mistake, we cannot backtrack it, right? We cannot backtrack it, right? That is not allowed once you have decoded to a certain level. So the right, so this is the issue that beam search has. Can we improve on it is the question that is being asked in the paper. So let's see how do you do it. So a simple solution for this would be that if you even if you have generated this, you should ideally be allowed to backtrack and go into this particular path, right? But that would require you to totally create this tree in the forward, that is forward direction, that is in the future, right? And that will exponentially blow up, because the number of tokens after any particular sentence would be equal to the amount of vocabulary. So it will blow up as you increase the depth of this beam search, right? So how do we go about it? So there is a standard practice for handling this, that is called MCTS, which is Monte Carlo Tree Search. If you do not know about it and want to know more about it, you can check out my previous video. I'll leave a link in the description. Okay, so I will briefly again talk about how to use Monte Carlo Tree Search, right? So this is the diagram that completely summarizes their approach and Monte Carlo in general. So Monte Carlo Tree Search, let me just Monte Carlo Tree Search, or MCTS as famously known as. This standard method was used in AlphaGo also, by the way. So you can check out that also if you want, if you're interested in this method, right? So how do you do it? You have 4 stages in this. First stage is selection, second is expansion, third is evaluation, and fourth is backpropagation, right? So let's say you have generated a tree so far, that you have a starting character and you have a tree A and X, and A was selected, and then A equal to is the token that can be added, or for X, X comma can be the token that was added, right? So this is the current condition of a tree, where the nodes in the tree represent the tokens that you have generated. They have the partial sequence that you have, right? So if you follow a particular path, you get a partial sequence. For example, if you follow the leftmost path, you get the partial sequence of A is equal to, and if you follow the second path, you get X comma, right? Now in the first step, you have to select a particular node, right? So what will you do? You will travel down any path in the tree and pick a node that you want to expand further. In the case of beam search, for example, we selected the node that was in the top K, right? In this case, you do not do it. You simply select based on certain criteria. What is that criteria? We will revisit again. Right? For now, let's assume that there was certain criteria based on which you can expand a particular node, right? And let's say in this case, you decide that I want to expand the node A. Okay. In the second step, which is expansion, what you do is that you expand this particular node using a certain token, right? So you decide that, okay, I'm going to append comma to this particular token, and you get A comma, right, as the sequence, right? Now in the third step, you will evaluate the partially generated sequence that you have so far, right? How do you what is the value of this particular, how good is the partial generation so far? That is what you want to answer in the third step, that is evaluation, right? Why is that needed? Because you would want to evaluate whether A comma is better than A equal to or X comma, right? Now because these are partially generated sequences, you cannot execute this on any compiler. It will give you an error message, right? That the code is incomplete, or the code has some issues and all, right? So what do? You will use this particular partially generated code so far and expand it using the large language model. That means you will ask the LLM to write the code that would be coming after this particular token this partial sequence has been generated, right? And for that, what would you do? You would use the standard beam search for that, right? So that is what is being done in the evaluation step. So you will evaluate the possible sequences of sentences using top K based beam search, right? That is what they have written here, that suggests the next tokens, pass it through a transformer, and this transformer is being used to generate these next evaluation steps, right? Also, where do the next token come from in the expansion step? It comes from the transformer. Okay. Now, once you have done that, you will get a complete code. It may or may not compile again, but it is a complete code as per the large language model. And that particular code that was generated is having the same prefix, that means the starting part of the code is same as a comma, right? So now you execute the code on a publicly available test cases that were given to you, right? And you see how many of those test cases were pass and fail. Then that becomes a measure to identify the quality of the code that was generated using this as the partial partial prefix, right? Essentially, I mean the prefix of the code that was that is to be used, right? And then once you have a reward with you, that means how good the code was generated. If we have this as a prefix, you backpropagate it. And this is not the backpropagation in the deep learning setting. This is simple English word backpropagation in the fourth step. So what you do is that you tell that each node in the tree that whether a comma was successful or not. If a comma was successful, you will update some values in a, and then you will update some values in pd. And now you repeat this 4-step process again and again up to a certain point. Till what point? Till the point that you generate a end of sequence token, right? So this is the 4-step process that is being used. Now what we saw a problem with the beam search algorithm, right? We saw this particular problem that you cannot backtrack and revisit. Now in the case of Monte Carlo Tree Search, how does this algorithm solve that particular problem? Let's first see that, right? So in this case, what they do is that this selection step makes sure, right, that you can expand a node that had already been expanded on a particular path. For example, in the very first step also, we chose to expand a node called A, which was already expanded as A is equal to in earlier. So now after expanding this node to this particular setting, in the next time step again, we can pick X to be expanded, right? Or later on, we can pick A again and maybe add another token. For example, we can add another token A semicolon. I don't know whether it will be a good or a bad a measure. I do not know, and that will be based on the evaluation. These 4 steps, right? Once you have expanded the tree to a certain depth and all, you will pick that particular token or that particular sequence that gave you the best passing accuracy and so on and so forth. Okay, so that is how it solves the problem that was generated by the beam search, because it allows you to plan in the future and expand the already expanded nodes in with a different token, right? So now let's first see the algorithm in its full glory. Okay, so what they do is that for max number of rollouts, that means how many these 4-step cycles you want to do, you select a node as the root, right? You select the root as the starting node, then you execute the selection step, then expansion step, then you execute the evaluation step, and finally the backpropagation step, right? In the selection step, right, you use something called P-UCB select, which is a sub module that they have used. I will discuss it in a brief moment, right? Once you have selected a node to expand, you will use a large language model to decide what are the top k tokens that has to be that should ideally be expanded, that should ideally be added to the tree, because you cannot ideally add all of them because that would be the size of the vocabulary, right? And that is not feasible. Now all the top k next tokens are added to the tree, right? Create a new node here, right? Now once you have done that, you do a beam search on the node, particular node that we have selected in the selection step, right? Then you get the reward and then you backpropagate the reward through the tree. Okay, so now this can lead to a problem that this can be very expensive, right? But the point here is that one trick that you can use is that once you have expanded a particular tree, you can reuse that tree in the next step. That is one of the optimizations that you can use, right? For example, if you decide that I'm going to go with a comma, right, in as a foolproof code, then in the next step, when you are trying to do an MCTS with the root node of a comma, you can simply use the partial tree that was generated below a comma. That is one of the optimizations that you can do. Second optimization that you can do is that this beam search submodule and this top K submodule are using the same large language model, so they are going to share some part of their generation, right? For example, beam search also uses top K, so you can leverage that, right? So you have to cache it. That is one of the optimizations that they are doing, right? So this is for this is shown in this figure 3, that at iteration t, for example, you tried to expand evaluate a comma, so you expanded all of these, and using beam search, where beam was equal to k is equal to, let's say, I think they have used 2, okay. And then when you have actually selected that, okay, I am going to pick any one of these, so you picked a comma b, right? Now a comma b's subtree was already created during the beam search already, so you copy pasted it here, so you don't have to reuse it, you can simply cache it, right? So this is the optimization that they are doing. So that's all for this particular paper. I'm not going to go through the empirical evaluation, because of course the paper was published in a star conference, so the numbers would have been great, and that like you can go through these in your own time. One thing that is left right now is the what is the selection criteria that they use. So let's go through that briefly. So they use something called upper confidence bound that was discussed in the last video, last video. So if you recall, if you have not have if you want a detail on that, please check out that video, otherwise I'll explain what they have done. Okay, so they say that P-UCB SA, that means partial code generated and the next possible token A. So for example, it would mean A comma, and this would be it would be B or equal to or semicolon or something of that sort, right? So they say that that will be equal to the QSA, that is the value of the action given the particular state so far, right? Plus some beta of S, right? And beta is the weight of exploration. That means you want to, so what happens in the MCTS tree is that, let's say you define a tree again and again, right? Some of the nodes will give you a very high value, for example, and some of the nodes will may give you a very low value. For example, you may have a high value for a let's say a equal to 1, but for a node like a equal to semicolon, the value should ideally be very low, already be very low. But it may be the case the value is low because you haven't explored it well enough. So you have to do a trade-off between exploration and exploitation, right? So that's what this UCB algorithm does. You can check out the video. Again, I'm shamelessly plugging my own video, or you can check a Wikipedia page also. So this is the exploration constant that you can control. And then there is this particular term. What is this particular term? This particular term says that if you have visited a particular node more, right, then this particular value will be very high, right? If you have visited that particular node that you want to expand, and divided by the number of times you have visited the next particular node that was generated after A action was executed on A. So this balances, essentially balances that how many times you have visited a particular node. So should you explore or should you not explore, right? And this is again weighted by what does the transformer think. In the original UCB, this particular term does not exist, right? And only this time variant exists, right? Time in the sense of expanding the tree, how many iterations you have done and all. But this says that how do you value a particular token based on the LLM that you are using. Okay, so based on this particular term, which is exploitation, because you have learned this QSA based on the experience that you have gained while expanding the tree, and this particular term which is exploration, That means how many times you have actually tried that action versus ignoring the value of that action, right? And this is again weighted by what does LLM think, right? So this is a trade-off between all these methods, right? So that's how they do the selection. So I will close this video again. If you have any questions, leave a comment. I will try to answer that. Thanks.